Okay, this is the second slide pack for our chapter 9 on Lewis structures. And so what we finished last week was we started to draw Lewis structures for covalent bonds. And so I wanted to talk a little bit about why this is good for covalent bonds and why it might struggle. So where our model, our Lewis theory model, where it might be limited versus our reality. And so Lewis theory implies that our combinations should be, that some combinations should be stable and others aren't. And our stable combinations are going to be things that include what we decided to call octets or duets in the case of hydrogen. So let's just predict the formulas and also how they're connected. Now, we can see that because hydrogen and our halogens, both of those are duets, they're diatomic molecules, and that's predicted by our Lewis theory. Oxygen normally forms two single bonds or a double bond, which is also predicted by the Lewis theory. So overall, our stable compounds seem to do follow along with this, but there are some stable bonds that might break those octets. Things where oxygen might have only a single bond or where it has a triple bond, but it still has an octet. An example of that might be like hydrogen, or an example that's just kind of showing some of this is things like our water here or our hydronium ion here. Right? And so we have some cases where our oxygen can go ahead and this one has 9 electrons, so it's actually breaking that octet. This is hydrogen peroxide down in the bottom right. And so overall, the theory does seem to do a fairly good job about anticipating our different compounds, though there are some compounds like this one here where we can break that octet rule. So it's not a rule that's where only compounds that satisfy the octet can exist. The second part about Lewis theory is that it implies that the covalent bonds are directional, so that they're shared between two specific atoms, unlike an ionic bond, where it's kind of an electrostatic attraction. That means that Lewis theory predicts that our covalently bonded molecules will produce molecules instead of like lattices, like an ionic one. And that's exactly what we see. We do see that our compounds containing just nonmetals generally make molecule units as well. The melting point and boiling point of our covalent compounds should be relatively low compared to that of our ions, of our ionic structure. And that's because we're just breaking the attraction between the molecules, but we're not actually breaking the bonds between the atoms. So the covalent bonds are strong, but the attractions between the molecules are generally weak, which is what we're going to get into in the next couple of weeks when we talk about intermolecular forces. And so we anticipate that our molecules should have lower melting points, which is fairly true. Generally, they're less than 300 degrees Celsius for their melting point. And we find them in all three states. So instead of ionic compounds where we only really find them as solids, and very rarely do we find them as liquids and definitely not gases at room temperature, molecules we can find as solids, liquids, or gases. And this is because they have strong covalent bonds within the molecule, but they have weaker attractions between the molecules. This gives us the ability to have a lot of different types of physical properties. So the hardness and brittleness of the molecules can vary depending on those attractive forces between the molecules. And so we do see that. This is different than our ionic compounds, which have much stronger inter-ion attractions. And so we don't see as large of a variety. Because there's no ions present, there's no charged particles, then our covalent bonds shouldn't conduct electricity in solid or liquid state. The only one that does are molecular acids when they are dissolved inside of water, because they begin to ionize within the water and then they form those ions. But if we have a pure acid, like what we saw with that glacial acetic acid, it doesn't form any ions, and so it doesn't conduct electricity, which is why its conductivity was so low. Lewis theory also predicts that the more electrons two atoms shares, the stronger the bond should be. And so if we start to measure the bond strength by how much energy must be added to break it in half, we can start to see that triple bonds are stronger than double bonds, and double bonds are stronger than single. The struggle, though, with Lewis theory is that it predicts that double bonds should be twice as strong as a single bond. But when we started to measure the amount of energy required to break a double bond versus a single bond, we found out that that is not true. They're not actually twice as strong. They are stronger, but not twice as strong. Lewis theory then also started to predict where a shorter bond should be when we're comparing bonds to like atoms. So the more electrons two atoms share, the shorter it should be. And so this does start to hold true. Triple bonds are shorter than double bonds, and double bonds are shorter than single bonds. But bond length is also determined by the distance. And when we talk about bond length, we are talking about the distance between the nuclei of the bonded atoms. Now, the single versus double versus triple is an important concept, with the triple being the shortest one. The other part to remember, though, is that the number of bonds isn't the only factor in determining bond length. The other part is the nuclei size. So a larger atom will have a longer bond length typically than the smaller atom because they can't get as close because of all of the electrons, core electrons, as well as those nuclei repulsions. So as a little bit of a recap before we add on to this, let's go ahead and let's write out the full electron configuration for phosphorus. How many valence electrons does phosphorus have? How many electrons does phosphorus need to complete its octet? And then how is it going to go out and find those electrons? So phosphorus should have this electron configuration: 1s2, 2s2, 2p6, 3s2, 3p3. The phosphorus has 7 valence electrons. Oh, sorry, not 7, it has 5 valence electrons. That's the 3s2 and 3p3. That means that it needs 3 electrons to complete its octet, and it's going to get those by forming bonds with other elements. Now, those could be ionic bonds, those could be covalent bonds. That's what we're going to be doing. Our next question is, I put up the answer here, but we would have been talking about why don't 2 helium atoms form the molecule He2 when brought next to each other? And when we look at that, helium doesn't have any unpaired electrons. Helium is in a duet. It only needs 2 electrons in its outermost ring. And so it's got the correct number of valence electrons according to the octet rule. And so it's not going to go out there and create a new bond with another helium atom because it already has all of the electrons it needs. Now, what I want you to do is I want you to draw out your Lewis structure for CNS. So that's carbon as your central atom, nitrogen, and sulfur. Now it has a 1- charge, so make sure you add in an extra electron. And so we should walk through that process. Now, there's a couple of different options that we could have drawn down here below. One of these is going to be the best option compared to the other ones. But if you look at them right now, all of them satisfy the octet rule. We have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Right? So in each of these molecules, we're satisfying the octet rule. And so we're going to figure out how we can choose which one is going to be the best, because there should be one best structure and then other options outside of that. So to do that, what we need to talk about is we need to talk about formal charges. Formal charge is the charge of an atom. Is the charge an atom would have had if all the electrons in the covalent bond were shared equally. So the formal charge is your number of valence electrons minus half of all the bonding electrons minus all of the non-bonding electrons. So we're going to use carbon dioxide down here as an example. Our oxygen starts off with 6 valence electrons. That's how many it should have. It has 4, so we're looking at our oxygen here. So we have 6 valence electrons. We're going to subtract from that half of the bonding electrons. So we have 2 double bonds. So that's 4 bonding electrons, so half of that. And then we have 2 lone pairs, which is 4 non-bonding electrons. So we get 6 minus 2 minus 4. And so we get a charge of 0. So its formal charge is 0 down here. Carbon, on the other hand, carbon has 4 valence electrons, right? And we're getting those valence electrons just from your periodic table. Those 4 valence electrons, it's got 2, 4, 6, 8 bonding electrons. It has no lone pairs. So we get 4 minus 4 minus 0. And so we're also getting 0 for its formal charge as well. Our other oxygen we would have to measure as well. It just happens that it looks exactly like our first one. So it's got 6 valence electrons minus 1/2 of its 4 bonding electrons minus 4 of its non-bonding electrons. And so that gives us a total charge of 0 as well. Now we're going to compare that with this other alternative structure on the right-hand side. That's carbon dioxide as well. But you can see that instead of having 2 double bonds, we have a triple bond with 1 oxygen and a single bond with the other oxygen. And so we're going to compare this. So our first oxygen, oxygen 1 on the left, it still has 6 valence electrons. It has 1/2 of 2 bonding electrons, and it's got 6 unbonded electrons from its lone pairs. And so it ends up with a formal charge of -1. That tells us that if we were to split each of those covalent bonds in half, it kind of has more electrons than they should have started with. It's got 1 extra one, giving it that -1 charge. The carbon in the middle is still 4 valence electrons, minus 1/2 of 8, minus 0. So it's still got a formal charge of 0. So it's still balanced in the amount of electrons associated with it. But that other oxygen, the one on the right, oxygen 2, it's got 6 valence electrons, 1/2 of 6 bonding electrons, minus 2 for its lone pair. And so that's 6 minus 5, and so it ends up with a +1 charge. So when we compare these, our formal charges is kind of telling us where our electrons have gone because of the bonding to give us an idea whether we have more or less than usual. And in this case, the oxygen on the left has 1 more electron than it started with, and the oxygen on the right has 1 less. Overall, our formal charges should equal the charge of the molecule So when we go back to our CNS and we look at our formal charges, all of them should add up to be equal to this charge here, this -1. -2 plus 1 adds up to -1. -1, 0, 0, -1, 0, 0, -1 adds up to -1. And so how we use formal charge to help us decide which of these structures is the best is that we want the one where our atoms have formal charges closest to 0. So we want the lowest total amount of formal charges. We would also like, we would like the lowest values of our formal charges. We also want the fewest number of formal charges. So if we can go to from 2 atoms having the formal charge to just 1, we would prefer the one with just 1. But if we have the option between a -2 and 2 -1s, we're going to go with the 2 -1s. And then the last part is we're going to put the negative formal charge on the most electronegative atom. So between our nitrogen and our sulfur, one of those should be more electronegative than the other. And in this case, it is going to be our nitrogen. So when we have to choose between these 2 structures, whereas right now we know first off that this one over here on the left is going to be our worst option because it's got a -2 charge and a +1. So we can do better than that. We can reduce our total amount of charge by just having a single one with a -1 charge. So this is going to be our worst, so we can get rid of that. When we're choosing between these 2, then we need that negative electron on our most electronegative atom. And in this case, that's going to be our nitrogen. which is more electron negative than our sulfur. And so this should be our best Lewis structure, and that's what we would be looking for. Now, this is helpful for us when we can make more than one of those options. And so I want you to try that again. We're going to try that with our nitrate ion, so NO3 minus 1. And then I want you to choose which one is going to be your best. So we should have nitrogen in the middle. We have a total of 5 plus 18, so that's 23 plus one more, so we should have 24 valence electrons. That gets rid of 6 of them, so we have 18 left. We're going to add on from the outside. And that got rid of my other 18. So the problem with this structure right now is we're still missing some electrons from that nitrogen. So I got to go ahead and move 2 electrons over. Turn that into a double bond. Oh. And now that's all satisfied. We should bracket this and put in our charge. And so that's one of those possible Lewis structures. But you might have drawn another one. It might have looked like this. And if we look at our formal charges, what we're seeing is that our nitrogen is positive because it should have 5 valence electrons. It's got 1/2 of 8, and so it's got a +1. Our oxygens, this one is a 0, this one is a -1, this one is a -1. Because those oxygens have 6 valence electrons, 1/2 of 2 bonding electrons, and 6 lone pairs. So that's where we're getting the -1 from. But that looks the same for all of these. So our formal charge by itself is not going to be able to tell us the difference between these different structures. We even have a third structure that we could have where that double bond is over on the left-hand side. And what that is called is that's called resonance. Resonance means that we have multiple options where they're just as likely as the other. And so the idea is Lewis theory localizes the electrons between the atoms that are bonded together, but we do have this concept that there's some delocalization of it. Delocalization is important because it actually makes the molecule more stable than we originally would have thought. It helps stabilize the molecule because it helps delocalize and spread out that charge. So instead of one atom having to hold that extra electron, each atom can hold kind of half of it. So resonance structures are when there's more than one Lewis structure from a molecule, and the only difference is the position of just the electrons. So they're still connected in the same way, but where those electrons are has changed, right? So instead of having the double bond with that nitrogen to the right, or with the oxygen to the right, we had the double bonded to the oxygen below. Right? Or down here, instead of being the double bond on the left, we have the double bond on the right. The actual molecule is going to be a combination of those resonance form. It's going to be that resonance hybrid. So it's not that it necessarily bounces back and forth between the two. It's just that it is drawn one way or the other because of the limitations of our Lewis theory. Instead of being a double bond and a single bond, our molecule really has something like a 1.5 bond on both sides. But we can't draw that with Lewis structures, so we just draw the two options and we showcase that. So you can kind of imagine that our two resonance structures, our double bond to the left or a double bond to the right, comes together to form this hybrid structure here. So this only happens when one Lewis model can't accurately depict a molecule by itself. So we have to show that combination. And this helps explain why some compounds are extra stable compared to other ones, because there's that delocalization of those electrons. Those electrons get shared by multiple atoms, which makes it a little bit more stable. So the rules for resonance structures is that they have to have the same connectivity. That means our atoms have to be arranged the same way. They have to have the same number of electrons. And while they can have expanded octets, which we'll get into a little bit later, we do want to make sure that our formal charges are being the same. So we should have the same formal charges in all of our options. So when we go back to look at our nitrate options, you can see here that each one of these is a resonance structure of the other. We're still connected the same way, nitrogen to the 3 oxygens, same setup, same number of valence electrons. The only thing that's moved is we've moved those electrons. We moved them from the lone pair to form the double bond. We moved the double bond to form a lone pair. These two are not resonance structures. Their formal charges are not the same. So when we look at them, while they have the same connectivity, the difference is that when they were all single bonds, we had a +2 charge on that sulfur, and then we have -1s on our oxygens. So when we're trying to look at our resonance structures, in order for them to be the same, they all have to be just as likely to happen. And in order for them to all be just as likely to happen, they have to all be the best. This one is not as good as the structure below, because the structure below has fewer formal charges, right? It actually has no formal charges, which is what we would prefer. So when you evaluate your resonance structures, it's better to have smaller formal charges, fewer formal charges, and have the negative formal charge on the most electronegative one. Our best structure should minimize the number of atoms breaking the octet rule. And we're going to talk about how you can break the octet rule in just a second. Now, the octet rule can be broken in kind of 3 ways. The first one is that you have an odd number of electrons. If you have 11 electrons, there's just no way you can satisfy the octet rule, because someone is going to have either 1 extra or 1 short. Our ions or molecules might have less than an octet. And this happens because maybe we don't have 8 electrons total. It might happen because of the electronegativity difference between them. The other one, which is the most common way that we kind of break our octet rule, is ions and molecules might have more than 8 valence electrons. This is called an expanded octet. Now, there are restrictions about who can expand, so we want to make sure that we talk about that. So the first one we talk about is there are fewer than 8 electrons. Elements in the second period before carbon can make stable compounds with fewer than 8 electrons and aluminum. So what we're talking about, it was talking about beryllium, boron, and aluminum are pretty much the only ones that make these exceptions. An example of this is BF3. We might say that BF3 existed like this with a double bond of our boron to our fluorine in order to satisfy that octet rule. But when you go through and you look at your formal charges, this boron would have a negative formal charge, this fluorine would have a positive. So what that is saying is that our boron is taking electrons away from our fluorine in order to satisfy that structure, which doesn't really make sense when we think about the electronegativities. Fluorine is much more electronegative than that boron, And so the fluorine shouldn't be giving extra electrons to the boron in order to satisfy boron's octet. And so when we experimentally follow up on this, what we find is that their bond lengths match much more with it being a single bond than it does with them being a double bond. So this tells us that our primary or a dominant Lewis structure should be this single bond one. So you can find this if filling the octet of the central atom results in a negative formal charge on the central atom and a positive one, then you don't have to fill the octet only for beryllium, boron, and aluminum. We would rather have that incomplete one than we would have the charges flipped. Another example is try to draw out your Lewis structure for AlH3. When we have, this should be more than 8. When we are in elements in periods 3 through 6, so that means something higher than period 2. So period 3 starts with our sodium. It's that row there. Period 3 means that we have an energy level of n equals 3. That means that we now have d orbitals available. This is an important part because these d orbitals allow us to make more than 4 bonds. Because there's now these new orbital shells that we can expand into, we can create more connections there than we would have been allowed before. An example is that PF5 does exist. PF5 means that this phosphorus is connected to 5 things, which means at a very minimum, it has to have 10 valence electrons. And so normally we would say that doesn't happen. But because phosphorus is in the 3rd energy level, it does have these d orbitals. And if you look at phosphorus, phosphorus has empty d orbitals for it to move into. There's been no electrons in that d shell. So when phosphorus starts to connect to these fluorines, it can expand out into those d ones to actually form all 5 bonds, giving it 10 valence electrons. We see this show up inside of resonance structures as well. Let's say that we're looking at phosphate. Phosphate is PO4 3-, and so we get kind of an option that looks like this versus one that looks like the one on the right. So if we weren't worried about our octet rule at all, the one on the right would be our better structure because our charges are less. Right? When we look over here with our formal charges, the one on the right has 3 oxygen atoms, each one with a -1, compared to the one on the left where we have 4 oxygen atoms with -1 plus a +1 on the phosphorus. So that double bond helps us remove formal charge. Now, in order for this to be the better structure, we have to make sure that phosphorus can expand. So we look at phosphorus, it's in the 3rd energy level. And so it does have empty d electrons, and so it can expand. If this had been a nitrogen, and we wanted to do a similar structure, could we? And your answer should be no, because nitrogen is not in the 3rd energy level. It's in energy level 2. And so it doesn't have a d orbital. So no expanded octet for our nitrogen. So while it's important to know that this starts in period 3, what I'm really looking for when I'm asking for why things can form expanded octets versus not, is I'm looking for you to tell me about this d orbital, right? The d orbital is the extra empty orbitals that those extra bonded electrons move into when we start to form these new structures. The last part is going to be our odd numbered electrons. So an odd numbered electrons might be like nitrogen monoxide, NO. Nitrogen monoxide, we have 5 valence electrons from our nitrogen plus 6 from our oxygen, so we have 11 valence electrons. So when we start making that structure, we might put 1, 2, 3, 4, 5, 6 on the oxygen. 1, 2, 3, 4. So that's 2, 4, 6, 8, 10, 12. That's 1 too many already. Here we go for our 11. Means that we have to have a double bond here. 2, 4, 6, 8, 10, 11. Good. Our oxygen satisfies that octet. Our nitrogen does not. And so when we're looking at this, as we're trying to compare those, we might have also thought, well, why don't we put a triple bond instead? Or why don't we leave the opening on our oxygen instead? Now, each of those can be classified out based on different rules. This one's our easiest one to throw out, and we can throw it out because nitrogen is not in the 3rd energy level, so we can't have an expanded octet. So we can toss that. Between these two, one way for us to tell this is to look at our formal charges. So our nitrogen's formal charge is 5 minus 1/2 of 4 bonding electrons minus 3 non-bonding electrons, and so it has a charge of 0. Our oxygen is 6 minus 1/2 of 4 bonding electrons minus 4 unbonded electrons to give us a charge of 0. The last part is then to compare it with this one down here. Our nitrogen down at the bottom right one, it has 5 valence electrons minus 1/2 of 4 bonding electrons minus 4 unbonding, so it gets a charge of -1. And our oxygen is 6 minus 1/2 of 4 minus 3, and it gets a +1. So when we look at those, between those two options, then we know that this must be our major resonance form because it's got our lowest amount of formal charges. And so that is what we're going to go with. So as we start to now go through and do our Lewis structures, we do want to go through and add in our formal charges. So when you start to draw them out, if we are going to do something like our NO minus, we would have our nitrogen connected to our oxygen. We would have the minus charge indicated, as well as all of our brackets. Now, in this case, think about whether that should be our best Lewis structure, or is there a better one that we could draw? So we're going to stop there for now. I'm going to add in the second section on this next part where we talk about our bond enthalpies to finish up today's lecture. But I want you to focus on doing your Lewis structures first. And so I want to stop now so that way you guys can get some time to practice these, and then also to go and start working on your lab now, because now you have the information to do the rest of it as well.